Okay, so my name is Stuart Ritchie. I'm the field engineering supervisor for Western Canada and the Pacific Northwest. And first off, I wanted to thank everybody for jumping on the call. We understand time is money in this industry, and you're giving us a decent chunk of your time to learn Sysmac Studio, and we appreciate that. So this is going to be a 5-part webinar series. So part one today is basic setup and programming. That's essentially taking your PLC from the out-of-the-box state, adding your I/O cards, adding some network distributed I/O, and creating a simple program and simulating it. Session two, which is on Thursday this week, September 26th, we'll be going over HMI programming. So we're going to take that project that we made today, and we're going to make an HMI interface for it. Part three on October 1st is intermediate PLC programming. So we'll go back into the PLC side and we'll dive into some of the more intermediate PLC features like importing libraries, using structures, UDTs, if you want to call them that. And then part four on October 3rd, we're going to dive into networking. So focusing primarily on Modbus and Ethernet IP, but we will touch on OPC UA if we have time for that. And then part five is an optional session. This is basically where you can come with any programming questions or issues that you might be having, and we can work on those. We'll also have most of our team on the call. So if you had an opportunity or an application that you're working on, we can discuss things kind of outside of the box, opportunity specific, that sort of thing. So it's an optional session, but it might be useful if you've got an upcoming project. So on today's agenda, we've got a little bit of housekeeping, a quick Omron portfolio overview, and then we're going to dive into Sysmac. We'll go over the startup screen and how we do file management. Then we'll get everybody to create a project and select their CPU. And then we'll go over the software layout and the IDE real quick. Then we'll have a quick EtherCAT demo. So this is something that I'll do on my end, since it's a safe assumption you don't have an Omron PLC and a bunch of EtherCAT devices sitting next to you. Then before we start crunching code, we're going to talk about some PLC specifics. Now, these aren't Omron PLC specifics, but these are things that might be done a little bit differently in the Omron ecosystem versus what you might be used to. Then we'll dive into some programming and we'll make our list station program. So some additional Omron attendees. They won't be on every single call, but they should all be hopping on at some point or another. So we've got Paul Hunker, who's the account manager out of Seattle, Matt Ryan, who's our DSM out of Portland, Connell Mahal, an account manager out of Edmonton, Wilson Packengan, who's an engineer out of BC, Logan Lyberg, who's a TSA out of Seattle, and Gersha Sadhu, who's an account manager out of Vancouver. So this training is for engineers, programmers, and SIs who are new to Sysmac but are not new to PLCs. So we're not going to be going over how many bytes are in a reel. We're not going to be going over typical program architecture and ladder logic basics. This is to tell you what you already know in other platforms and show you how to do what you already know in the Sysmac ecosystem. So by now you should have Sysmac installed and open. We're assuming you have PLC experience, primarily ladder logic experience, and we're assuming you're mild to moderately caffeinated. So that's a humorous way of saying that this will be fast-paced. We will not be taking breaks. We want to make the most of your time and cram as much content into this hour and a half as we can. Please keep yourself muted. Post questions in chat whenever you can. We will have question periods where we pause to do things. I'll check if anybody's having any issues along the way. So there will be times where you can speak up, but you're welcome to post any issues or screenshots in chat if you're having some issues. And at the end of the class, if your project is just full of bugs, full of errors, it's just not compiling, whatever, don't feel like you can't jump on the next session. We'll send out a completed project after every class that you can open up and start right from where you left off for the next session. And if you have an external monitor, it will be very beneficial. I'll be doing a lot of exercises where I'm demonstrating something in ladder logic, and you'll need to essentially replicate that on your end. So you'll have a few minutes here before we actually start doing things in Sysmac. If you've got an external monitor in the other room, now would be a good chance to grab it. It will be very beneficial. And finally, we have official instructor-led training. This is a condensed engineer-led version. Our training classes are 2 to 5 days long. They're usually in Chicago or Toronto, kind of depends on the course and the time. If that's of interest and you want to progress your training after this, you can ask your account manager or your distributor about that. So now this is something that we're going to do only on the first session. And much like how you sometimes have to watch an ad video to watch a free YouTube video, we do have to throw in a quick little sales pitch here on some Omron solutions for the free Sysmac training. I think it's fair. So we're not going to spend a ton of time on it. It'll be short and sweet. Automation control systems, as most of you know, you're here for PLC and HMI training. We also have motion controllers in this category. We have a lot of visualization options from SCADA to HMIs to IPCs. Control components, something we're pretty well known for, temperature controllers, panel meters, power supplies, that kind of thing. Switching components, push buttons, limit switches, general purpose and safety rated. On the machine safety front, we have quite a huge portfolio from light curtains to laser scanners to safety PLCs to safety monitoring relays. On the robotic side, we have a lot of different robotic options from articulated arm to SCARAs to Deltas to cobots to AMRs, servo drives, VFDs. In the sensor market, we're a pretty big player, so proximity, photoelectric, and we're grouping vision into this as well. So machine vision, we do quite a bit of, and we have a large portfolio of machine vision as well for inspection type applications. And then on the traceability sensing front, we do a lot of code reading, RFID, that kind of thing. Now, Sysmac is actually an acronym. It's System for Machine Automation Control. So we are very invested in EtherCAT, which we use as our device level network. So motion, safety, vision, I/O, and sensing would be a good example of something on the device level network. And we also have on all of our NJ and NX PLCs, Ethernet IP, which is much better for a data level network, like your visualization or cloud connectivity, that kind of thing, controller to controller communication. But Sysmac is a truly integrated architecture. So our philosophy is we have one piece of software, we have one project file, we have one controller, although you may have many, but we have one connection that lets you access and configure all of that. And most importantly, everything in your Sysmac system is going to be saved on one project file. So you could have your safety CPU, your drive parameters, your multiple PLCs, multiple HMIs, that kind of thing. Makes it easy to manage, especially when it comes to change management. This is the current portfolio of the NJ and NX CPUs. And they're the CPUs we program with Sysmac Studio. So we're primarily focusing on the NXs today. NJs are kind of more for retrofit type applications. Bottom left, we've got our NX1P shoebox style PLC. It generally has 24 to 40 built-in I/O, and you can expand it with NX I/O. And then as we move up the line, we get more I/O, we get higher memory, faster speeds, right up into the NX5 and NX7 territory where you can control 256 servo drives with a single PLC, integrate with SQL databases in the cloud. Lots of performance on those high-end controllers. This is just to give you an idea of kind of how they vary as you get higher up. So, if we're looking at an NX1P2, 3.3 nanoseconds per instruction, NX7 is 0.37 nanoseconds per instruction. So, almost 10 times faster, significantly more memory. We're not going to spend a ton of time diving into the specs, but NXIO is the IO that we've standardized on for the NX PLCs. So we can have it locally on our CPU, or we can have it on a remote rack, either EtherCAT or Ethernet IP. There's even third-party compatibility. If you have it on a remote rack, a lot of customers like to cut down on their I/O cost with Ethernet IP I/O instead of local I/O. So lots of options out there. And the different flavors of I/O, I mean, of course, we have our basic digital and analog, but we get into some pretty specialized I/O, which can add capabilities to systems that don't natively have it, like I/O link, RFID, load cell, temperature control, high-speed counter, pulse output for motion control, that kind of thing. So lots of different flavors of NXIO that we can add to our projects or third-party PLC's projects as well. This is the last one here. So a relatively new product that we recently released is called our RT1. So it's a cellular or a wireless access gateway. It comes in a few different flavors. We have cellular, Wi-Fi, or LAN only connectivity. And this is a way to remotely program your PLCs, HMIs, automation equipment in general. It's not in any way, shape, or form tied to Omron PLCs only. We can do pretty much any PLC or piece of equipment out there that has a USB, Ethernet, or serial port on it. So in addition to remote programming, we can also use it for SCADA applications and set up tunnels to pass that data back to your SCADA system. So, okay, sales pitch over. Thank you for sitting through that. Now we're going to talk about the Sysmac Studio startup screen. So everybody should have seen this already when you opened up your Sysmac Studio. So you don't need to open yours and play along with this. I'm just going to be touching on what these different parts of the startup screen are. So from top to bottom on the left here, we have the project management. So obviously we can create a new project or we can open an existing project. We can also import and export projects as we need. So normally when we save a project in Sysmac, it's saved in an internal directory. And if we ever want to bring in a new project or pass that project off to a colleague to work on, we can import and export it. There is a feature now where we can work directly from the project file. So if your company is operating off of a shared drive somewhere, you can actually work directly off that SMC2 file, and it will save any changes to that SMC2 file. SMC2, as I'm sure you assumed, is the file format for Sysmac Studio projects. Next on the list is connect to device. So if we encounter a PLC and we want to connect to it to generally pull the program off of it and make some changes, this is where we do that. So we can choose the type of device it is. It could be a PLC, a drive, a safety controller. Since we're focusing on PLCs today, with controller selected, we've got the different options to connect to the controller. So some of our controllers have USB connectivity. All of them have Ethernet connectivity. Now, there are two options here, which I should talk a bit about. So direct connection via Ethernet and Ethernet connection via a hub. So the direct connection via Ethernet is actually a really nice feature because you can connect an Ethernet cable directly from your PC to your controller, and regardless of the IP address, you can connect to it. So you could be on a completely different subnet, you could have DHCP enabled even, and you could still connect to that PLC. So if you've ever been to a facility and you find a PLC you don't know the IP address of, it can be a bit of a headache, and this kind of alleviates that. Now, Ethernet via a hub, if you need to go through switching infrastructure and you know the IP address of the PLC, this is the option you would choose for that kind of connection. Now, in the latest, or possibly the second latest update to Sysmac, we released something called the network browser. It's not so much we released it, but we made it accessible from this. So if you were ever curious what's on your Ethernet network, for example, you can browse it and it will show you the PLC, the IP address, the firmware version, the controller name, that kind of thing. So if you're looking at a cabinet, you can't get inside, but there's an Ethernet port on the side. This could help you visualize exactly what's inside on the Ethernet network. Now, finally, the licensing at the bottom here. So most of you are on the trial version. If and when you upgraded to a light license or a full license, whatever option you pick, all we would do here is register a license. You'd enter your license number and your software would be registered. If down the road you get a new laptop and you want to move this license off, you can deregister this license and register it on the new one in the same way. So Now I'll get everybody to play along with this part. So we're going to create a new project in Sysmac Studio. And at the very top left in our startup screen, we have the new project button. So I'll get everybody to click on that, and then you can fill in the project properties according to what I have on the screen. Obviously, the author will be your name, not my name. And it's going to be a standard project. The controller we're going to pick is an NX102 9000. And for what we're doing in this, the version is not important. I picked 1.40 because most people should have that as an option, even if you're on an older version of Sysmac. So I'll give everyone a second to create their lift station project. And once you've filled in the details and you've selected the controller, you can go ahead and click Create. Now, once you've created your project, it's going to bring you into the Sysmac IDE. So I'll give another 10 seconds here for everyone's projects to get created, sorry. And now that we're in the IDE, we're going to pause here for 2 seconds, and we're going to go over some things in Sysmac that might be different than what you're used to from a programming perspective. So I will get everybody to double check that these settings are set according to what I have on the screen here. So if everyone can go into Tools, Option, and there are 2 categories that I'll get everyone to navigate to and make the changes according to what I have on the screen. Now, I think the latest version, some of these have been changed to the way that I have specified. So if these settings match what I have on the screen, then you're good. Some of the older versions of Sysmac, these might be different, but these will make your life a lot easier if these settings are set according to what I have on the screen here. So just to show everybody how you get to those tools, option, and then from the categories here, we're going to be modifying the ladder editor category, and we're going to be checking off select local or global variable and register it. And then from the variables tab or the variables category, we want to change the variable name used in projects. And if anybody is having any issues so far, now would be a good time to speak out. I'm going to pause here to let everybody change those settings. Okay, does anyone need more time? Awesome. So the Sysmac Studio layout is similar to a lot of other development environments. I'll kind of work from top left to bottom right here. So the Windows menu at the top, you'll find typical things like file management, you save, that kind of thing. In the controller and the simulation tabs here, we'll be going in there quite a bit. This is where you could rebuild your controller. This is where you could start your simulator, but we'll be doing all these things today to show you. Now, the toolbar directly below that has shortcuts to probably 95% of the operations you'll need to do in Sysmac Studio. So transferring to controllers, synchronizing, turning monitor on and off, your troubleshooter, that kind of thing. So a lot of handy shortcuts in the toolbar here. Now on the left-hand side, we have the multi-view explorer. So we can have multiple PLCs, multiple HMIs, lots of different hardware in our project. So according to what's selected in the device list, which it's a little hard to see here, but it's directly next to the picture of the PLC. Um, Everything below it in the Multi-View Explorer will change according to the device you select. So if it's a PLC, which is what I have pictured here, you'll have the PLC configuration stuff available to you, like the IO map and your EtherCAT network. And it's essentially divided in two. The second half is the programming side of it. So all of your programs, your data types, your variables, that kind of thing, that'll all be accessible from the programming section of the Multi-View Explorer. Now, depending on what you have selected in the Multi-View Explorer, the contents of the main window, which we call the edit pane, will change according to what you have selected. The accessory windows at the bottom, you can see there are 3 tabs on this one currently: Output, Build, and Watch. So we can add different tabs to the bottom, and they will always be anchored to the bottom of the screen, and we can switch between them like you would in a web browser tab by clicking at the very bottom between, say, Output, Build, and Watch in this case. Now on the right-hand side, we have the toolbox. So depending on what you're working on, the toolbox will be populated with, in this case, programming instructions, because we're working on ladder logic. If we were setting up our IO rack, the toolbox would be populated with the different IO cards that we could add to it. So you'll be fairly familiarized with this one by the end of the day, but that's the basic layout of the IDE. Now, EtherCAT, I've mentioned it before, so we're pretty heavily invested in EtherCAT, and it's excellent for device level communications, especially motion control and IO. So you guys don't have EtherCAT devices with you, I'm going to assume, but I do have an Omron PLC next to me that is connected to some EtherCAT devices, so I can give you guys a 2-minute live demo of setting up your EtherCAT network and kind of how easy that is. So I'm going to go online with my PLC right now, and I have 2 EtherCAT devices connected to it. And I don't, if I don't have the luxury of having the hardware in front of me, I can set it up ahead of time. I have all these EtherCAT devices here that I could add. We play quite well with third-party EtherCAT devices as well, as you can see from my toolbox. But if I just want to find out what's there and add it to my project, I can right-click on the master, and I can do something called a compare and merge. And that's going to go out onto the EtherCAT network, and it's going to find everything present, and it's going to show me what's there. And if I want to add that to my project, I just apply the actual network configuration. And now both of those servo drives are in my project. All of the tags for those servo drives are in my IO map. So you can see here, I've got my control word, I've got my target position, my target velocity, that kind of thing. Now for local IO, we have essentially the exact same setup procedure. So we have IO cards that we can pick from for NXIO. But again, if you have the luxury of having those cards on the PLC rack right in front of you, we can do a compare and merge with that. And it tells me that I've got an EtherCAT interface that it's detected. It's got a digital output and an IO-Link master present. So I can go ahead and add those to my project. And again, these are now in my IO map, and I can drill down to this digital output card if I want, and I can assign a variable to output bit 0. So we will be doing this. You guys don't need to remember this. This is just a live demo of how easy it can be to kind of auto detect everything on your PLC once you've got it built. So now we're going to get into some of the things that Omron may do differently than the platforms you're used to. So we support ladder diagram and structured text, or ladder logic, it's commonly called. So we follow the IEC 61131-3 programming standard quite closely. One thing we do differently, and it's actually a huge advantage in many cases, is we can kind of have the best of both worlds. I personally prefer ladder, but there's lots of opportunities for structured text to save time. And jumping back and forth between a structured text routine and a ladder routine can be a bit of a pain. So in Sysmac Studio, we can actually embed structured text in our ladder logic, and we can conditionally execute it with ladder logic instructions. So This is really helpful if you need to crunch some array data, if you need to do some order of operations, if you need to work with a lot of dynamic index variables and multidimensional arrays. Ladder logic can make your life a lot easier, and not having to jump back and forth from a ladder routine to a structured text routine can really clean up your program quite a bit. So the way we do variables in Sysmac is we have internal and global variables. Now, when you create a new variable in your ladder diagram or your ladder logic, you'll get a little pop-up like you can see on the screen here that will ask you, do you want this internal or do you want this global? So the scope of internal versus global is kind of illustrated here. So if we have an internal variable, we can access it in any of the sections that are within the parent program. So in this example here, the demo move linear circular program has 4 sections. And if I made an internal variable in trajectory section, I could access it with any of the other 3 sections of that program. If I tried to access that variable in the demo gear in position program up here, it would not recognize it, and it would attempt to create a new variable because it would be foreign to it, essentially. Now, global variables you can access in any section of any program, and you can also use them for things like displaying on an HMI or communicating with I/O over the network, that kind of thing. So I tell people, when in doubt, make it a global, because you can use a global as a local, but you can't use a local as a global. Now, contacts and coils in Sysmac. So we have one contact and we have one coil, or one input and one output instruction. Now, we can do a lot of different things, like make it a normally open, make it a normally closed, but instead of having an object in our toolbox for each one of those conditions, we have one contact and we right click on it and we choose if we want to invert it or if we want to make it a one shot up or a one shot down, diff up, diff down, we call that. Same with the output. If we want to make it a set instruction, we just right click on it and make it a set instruction. So it opens up the toolbox quite a bit, and we'll be doing this to a lot of our contacts and coils in our program today. Timers in Omron. So we follow the IEC 611 time data type. So we specify that in days, hours, minutes, seconds, milliseconds, and you follow the order of the largest time increment to the smallest time increment. So all of our timers use that kind of syntax for the timer. And it's nice when you're looking at the elapsed time because it will give it to you in human readable format. Like you can see here, 1 minute, 57 seconds, 56 seconds. Now, the time data type doesn't play well with all visualization devices like HMIs or SCADA. So sometimes you do have to do some modifications to set a timer from an HMI, for example, but all of the timer instructions or anything related to the time data type has example code on how you do that, and we have instructions to support that within Sysmac. Constants in Sysmac Studio. So we generally need to specify the data type before we specify the constant value. So you can see in this example here, this is a real value, so you would type real pound and then the value. If you just type the value, it will complain about that. It will generate an error. Sometimes you might want to express a constant in binary or hexadecimal as well, and we can do that by specifying the data type, pound, the number base. This is 16, so hexadecimal in this case, and then the value specified in that number base. So sometimes you don't want to pull out Windows Calculator to figure out what the decimal equivalent of a binary number is. So you could actually enter it directly as a binary constant, and it will tell you, it will convert it for you, essentially. So that can be handy. Okay, so our tag attributes. So when we make a tag, we can look at our tag database and we can see that tag and the data type. Now, there might be some tag attributes that you aren't used to. So I'm going to touch a little bit on some of the Omron specific ones, or at least maybe some of the ones that you haven't seen on other platforms. So initial value is pretty self-explanatory. So this value will be written to the tag at startup one time, and one time only. After that, it will take on whatever value you give to it. The at column here, the AT column, so this we won't be looking at much today, but this is kind of it gives you an address if this is mapped to either an EtherCAT device or an IO card. It will give you the actual address of where that is in the system. That's auto-generated. You don't have to make that. One thing that you can use it for is an address. So our older PLCs had addresses, and to maintain backwards compatibility with some of the network protocols that they still use, we can actually assign an address to it. And then if a device were to ask our PLC for, in this example, address D100, our PLC would respond with this tag at this address. So this is something a lot of other platforms have for backwards compatibility reasons. Now, the retain attribute, again, pretty self-explanatory. Do we keep this value through power loss? Otherwise, it starts at 0 or false at startup if this isn't checked off. So any kind of set point that you don't want to have to enter every time you restart the system, give that a retain value. The constant attribute. So if you want to make a constant, it might be easier to use a variable instead of hard coding the constant in multiple situations where you're calculating something, for example. So if we check off the constant checkbox here, our program will not compile if we ever edit or attempt to edit that constant. We cannot access it over the network, and it's useful for some things. Yeah, I'm not gonna dive into it too much here, but the network publish column, this is for networking. So Ethernet IP and OPC UA. We'll touch on this in session 4, so these should be clarified a bit more on session 4. And a comment, of course, if you like to comment your tags, you've got that option there too. Okay, so data type requirements. We are pretty picky about data types in Sysmac. And it's an engineering decision that we made, because when assumptions are made and conversions are made, it can cause problems in some situations. So we are picky about data types. Now, if you mouse over any parameter on any function block or any instruction, it will tell you the data type it's expecting. If you put the wrong data type there, it will let you know, and you will not be able to download your project to the PLC because it has an error in it. Now, in some situations, you'll find obscure looking data types like this one I have highlighted here. Now, these are actually structures. So some inputs are structures, like this parameter set here would be a structure. I believe it's got about 8 variables internally to it. And when you create a variable, it will actually create it of the structured data type that you need. So it might look intimidating, but really it creates it for you. It does it for you. It just won't let you put the wrong data type there, is kind of the gist of it. Now, some instructions will take any data type, like the move instruction here. So you could attempt to move an integer into a real, but you will get a compilation error if you try to do that. So in this scenario, it will ask you for the data type when you create the variable, and you, as the programmer, need to make sure that it's a compatible data type with what you're working with. And finally, one last thing, there may be some new instructions you're not familiar with. If you click on any instruction and press F1, it brings up a great instruction reference with examples, with variable clarification in both ladder and structured text. So very useful if you're working with new instructions to just hit F1 and read up on the instruction a little bit. Or if you're having any issues, that might be the solution for you. Okay, now we get to dive into the fun stuff. So everyone can open up their Sysmac Studio now. Should already be open. And what we're going to be programming today is pretty much the world's simplest lift station. So there's essentially a control room and a lift station out in the fields somewhere. So we've got a couple buttons in the control room to start and stop our lift station, And then we've got the lift station itself out in the field, and we've run an Ethernet cable out to a remote rack at the lift station itself. So in the control room, we've got a start button, a stop button, and a reset button. Out in the field, we've got an analog tank level. We've got a motor that we can turn on. We've got a low level switch for pump protection. We've got a motor fault, so we make sure we don't, so we can notify people if our pump is tripped. And we've got an alarm beacon, so we can notify people who don't happen to be inside the building. Now, you don't need to screenshot this or anything. We'll make sure that you know where to map the I/O and lay everything out here shortly. So the first thing I'll get everyone to do is go into your EtherCAT network. So in your Multiview Explorer, under Configurations and Setup, the first item is EtherCAT. And if you double click on that, it will bring up your EtherCAT setup in the edit pane. And the toolbox on the right-hand side has now been populated with EtherCAT devices. So the first thing we're going to add is an EtherCAT coupler, we call it, which is essentially a way for us to get NXIO on the EtherCAT network. So I'm going to be developing this with you guys here. So in our EtherCAT network, we go to the terminal coupler category, and then we can grab an NX-ECC202, and we can just drag and drop it right on top of our master, and it's now added to our project. So I'll give everyone a second to do that. Does anyone need more time? Great. So now that we've added the coupler to our EtherCAT network, we can configure the coupler as far as what I/O cards are on it. Now, to drill down to the coupler and start building the cards on it, we can double click on node 1, NX-ECC202 in the Multiview Explorer. We could double click on that, or we can right click on the coupler in our EtherCAT window, and we can go to Edit Slave Terminal Configuration. So there's more than one way to get there. But now that we're here, our toolbox is populated with NXIO cards. So we've got all the categories of NXIO cards that we could put on the rack. And to keep things simple, I went with basically the first card in each of the categories. So the remote rack, which is on the bottom here, the first card we're going to add is an IA3117. So this is a digital input card. So if we go to the digital input device category in our Multiview, or in our toolbox, sorry, the very first card is an IA3117. So we can drag and drop this next to the coupler, or we can double click on it and it will insert it next to whatever you have selected. So the first card, digital input device, IA3117, the very top card. The next card on the list is the NXOC2633, which is a digital output card. So in our digital output device category, it is the very first card. It's a relay output card. And we'll drag and drop that next to our digital input card. And the final card we'll be adding is the AD2203, which is an analog input card. So I'll get everyone to go to the analog input device category, and it's the first card, the AD2203. So we have the first digital input card in the category, the first digital output card in the category, and the first analog input card in that category. Now, if you're worried you got the order of the cards mixed up, you might have accidentally dropped one in the wrong place, something like that. it's kind of hard to tell which card is which from these pictures. Now, if you mouse over, you will get a tooltip, but one thing you can do is right-click anywhere on that rack picture, and you can go to Show Model/Unit Name, and it will display the part number of that card. And then if you needed to reorganize something, you can just drag and drop it to the right place. If you're building a panel and you're curious how wide this rack is and you don't feel like digging through data sheets, you can click this little black triangle to the right of the rack and it will tell you how many millimeters wide that remote rack is. And that includes the end cap as well. Anybody having any issues so far adding those cards? Awesome. So next we'll do our local I/O. That's going to be on the CPU rack. So right below the EtherCAT category in our Multi-View Explorer, we have the CPU/expansion racks category. So we expand that, we have our CPU rack. We don't have any expansion racks. If we double click on our CPU rack, we're going to get all of the same NX-IO card options in our toolbox. Just we're adding them to our CPU now instead of our remote rack. So we're going to have the same digital input card and the same digital output card on our local rack. So the first one will be the digital input device, the IA3117 card. And then the next one will be the first card in the digital output device category, the OC2633. Anybody need more time with that? Awesome. So now that we have the cards set up, what we need to do now is go into something that we call the IO map, which is the next category down. And what the IO map is where we make the association between a physical device and a variable that we'll use in our program. So if we expand the ECC 202 and we drill down to the first card, for example, the IA3117, we have the 4 inputs right there. And we have a column that says variable, and we can type a variable there. So whatever variable we type here is going to be what we use in our program. So when it's true, when that variable is true, that digital input will be on. When it's false, that input is off. So this is for inputs and outputs. It works the same way. And the data type will be automatically assigned based on the data type here. So if we're looking at the analog card, it's an integer because we're getting an analog value. And for anything digital, it's going to be Boolean. So I have a slide now that I'll get everybody to essentially copy what's on that slide as far as variable names go, just so we all have consistency across our projects.
Do these Boolean variables, do they initialize as false every time?
Yes. Yes, they do. Even if they're retained, if it's assigned to an, yeah, they do initialize as false. If it's an input Boolean, it's going to initialize to whatever the initial state of that input is. So if this was a normally closed circuit and there was a true signal going to input bit 0, for example, it wouldn't matter what that variable initialized to. It's going to take the value of that digital input on the start of the first cycle kind of thing. But as far as outputs go, yes, they initialize to 0. Any other Boolean, unless it's retained, is going to initialize to 0. Did that answer your question?
Yep.
Okay. All right, so now we get to do some tagging of the various IO points in the system. So I'm going to leave this screen up. If you want to fill in the variable comments, you can. If you'd rather just use the example program that I send out after the class, it's going to have logic and variable comments in it. You're welcome to use that too. So I'll leave this on the screen. You can expand all of the categories in your IO map, and you should be able to tag everything that you see on the screen. And if anybody's having any issues, feel free to speak out. I'll give everybody a minute or two to do this.
Oh, hi. I have a question. Um, can you use structures into the IO mapping?
Not in the IO mapping, no. We can use them pretty much everywhere else, but IO mapping is elementary data types only. Okay, does anyone need more time? Great, let's move on. So our control philosophy for the lift station is as follows, and you don't need to screenshot this. We'll come back to it as we go here. So at startup, the plant is in stop mode. The start push button will place the plant in run mode as long as we don't have a low level and the motor isn't faulted. The stop push button will take the plant out of run mode, and run mode is a bit that we're going to generate as an internal kind of state tracking bit. Now, while we're in run mode, the pump will turn on when the water is above the high set point, and we'll have to make a tag for that. The pump will remain on until the water level is below the low set point, and we'll have to make a low set point tag for that. If the low level switch trips, stop the plant, flash the push button in the beacon, and then set an alarm bit true. So we want to retain that alarm in the event that the level switch recovers. We want to know that it actually happened because that's an abnormal state. When the motor's running and the motor fault input becomes true, we need to stop the plant, flash the push button and the beacon. The reset push button will clear errors if the conditions allow, and the LEDs on the buttons in the beacon will reflect the mode that the plant's in. So green will be running, red will be stopped, and if there's an alarm, we'll be flashing red on both the beacon and the stop button. So We're going to go through these one at a time and program them. And then at the end of the class, hopefully we'll have 5 minutes to run through the simulator and we can test this control philosophy. So what I'll get everyone to do is we're going to add another section to our program. So currently by default, we have program 0, section 0. So if you right click on program 0, you can add a section. And we're going to rename the sections. The first one, we'll call it analog, just because we'll need to scale our analog in that program. And the second one will be, we'll call it main_control. And so everyone can go to the analog program first. So when we get the value from our analog input, it's a 4 to 20 milliamp signal, but it comes in as a value of 0 to 8,000. And we need to get a tank level of 0 to 100% out of it. So we need to scale this analog input to our needs. So the very top of our toolbox has a category called analog conversion. And if we expand that, there's a function in there called scale transformation, scale trans it's called. So I'll get everyone to drag a scale trans block out onto their first rung. Now, if we mouse over the inputs on scale trans, we'll see that the input is a real. Our scaling parameters, our ranges are all real as well. It says any real, so we'll actually have to choose between long real or real. And then our output is a real as well. Now, in our I/O map, we have, I'm just going to zoom in a bit here for you guys. In our I/O map, if you guys recall, our analog comes in as an integer. So we need to convert that to a real, and then we need to pass it into that block so we can scale it accordingly. Now, data type conversion is a category in our toolbox. So we need to convert an integer to a real. So these are all alphabetical. If we scroll down, we should find int to real. There it is. And again, that's in the data type conversion category. So we can drag and drop an int to real in front of our scale trans block. And when we double click on the in for our int to real function, we can start typing and it should autofill. It will detect any variable that starts with the characters you're typing and the data types match. So that was tank level raw was our variable on our card. So start typing tank and it should detect that variable. We can double click on it or hit enter and it will autofill it for us. The color that it gives it tells us that this is mapped to a physical device. So you'll see some different colors on variables, and we'll talk a bit more about them on session 3. But our tank level raw is going to be converted into a real value. So we'll have to create a variable for that. So we'll call it tank level real. And we're just going to type it. And when we hit enter, it's going to ask us if we want this to be an internal or a global. Now, if you remember from the presentation, kind of the scope of internal versus global, we can leave this internal since this is just an intermediate variable. Now we're going to take that tank level real, and now we can pass that to our scale transformation block. Anybody having any issues so far? Good. So we can, and you often do, have variables for your scaling parameters. You might have a full scale value if you need to adjust a transmit or something like that. But to keep things quick, we're just going to use constants for our scaling parameters. So x0 is the input lower limit. So we're going to hard code 0 as the value since our input is 0 to 8,000. So if you remember from the PowerPoint, it's the data type pound the value. Y0 is the output lower range. That will be the same thing. Now the input upper range, we can check in our CPU rack. We can look at the card and we can see the range that we get, but it's 0 to 8,000. So our upper range is going to be 8,000. And that's our input upper range is X. Now the output upper range, we want to scale this 0 to 100%. So that's going to be 100. For the output of the scale transformation block, this is the scaled value that we're actually going to use in our logic when we're comparing the tank level with our set points. So we'll make a new variable for this, and it will be tank level scaled. And we'll make that a global since we'll want to add this to our HMI down the road. And if it asks you a data type, we've been working in real, so you're going to choose real as your data type. So give everyone a second to copy that line. Anybody need more time? Okay, great. So we are done with the analog section of program 0. So we're going to jump over to main control now. Now, if you recall from the control philosophy, it said at startup, which is the P underscore first run bit. That's a system bit, and I'll show you guys how to add it in a second here. The plant is in stop mode. So our run mode bit is going to be false. We don't want to turn on the power to the plant and just have it resume right where it left off. We want to make sure it's in the safe stop state when we start up. So the P underscore first run bit, for any of the system bits, we just take a normal contact, and in our toolbox, you can type C as a hotkey for it if you're a hotkey programmer. In our toolbox, there's kind of a one size fits all, a commonly used category, and that's ladder tools here. So if we expand ladder tools, you'll see an input and an output. So input is C, that's the hotkey. Output is O, that's the hotkey if you're a hotkey programmer. So we'll drag an input to the start of our rung. And the system variable we want, if we start typing P underscore, you can see a list of the system variables that are available to you. And we want first run. So we could double click on it there, or you can just type it out. So the first run bit is true for the first cycle of the primary periodic task, and then it is false forever after. So it's good for setting initial states and things. Now we want to reset the run mode bit. So we haven't made the run mode bit, but that's okay. We'll drag an output to the right-hand side of the rung, and this will be our run mode bit. So we'll call it run mode, and we'll create it as a global. me zoom in a bit for you guys. Now, if you recall, we have one contact and one coil. Now, if we want to reset run mode, we need to make this coil or this output a reset instruction. So we can right click on it and we can choose reset instruction. Now, there's another category at the bottom that says set/reset. That is not what you want. That's for simulating. We want the reset instruction, which is pretty much dead center when you right click on it.
Does the reset instruction mean that it's just going to toggle it once?
Yes, correct. Yeah, it won't. You can have multiple set and resets. It's not like the general output where you you have to be careful when you use it. But well, I should clarify that. It will reset it whenever the preceding logic is true. Since this first run bit is only true for one scan cycle, then it's only going to issue that reset command once. Okay, for our next rung, and we can add a rung by either R as a hotkey, or we can right-click on a nearby rung and we can choose to insert a rung above or below. So I'm going to insert a rung below. And the next condition of our programming exercise is the start push button will place the plant in run mode. We've got our run mode tag already, as long as the level switch isn't tripped and the motor isn't faulted. So in our ladder tools, I'm going to grab 3 inputs, drop them on the rung. You can copy and paste. You could hit C 3 times if you wanted to. And our start push button, which is start_PB. When that is pressed and we don't have a level switch and we don't have a motor fault, then we can go to run mode. So the level switch low tag is LSLL. And the motor fault tag is motor_fault. Now we want to invert these contacts because we want to make sure that they are false, meaning we don't have the level switch and the motor isn't in fault. So to do that, just like we modified the output, we're going to right-click on the contact and we're going to choose invert. If you're a hotkey programmer, it's just /. And now I'm just going to copy and paste Control-C and Control-V the run mode from the rung above and drop it on this rung. And then I can right-click on it and I can change to a set instruction. And that will satisfy that control philosophy condition. I'll give everyone a second to catch up. Is anyone having any issues? And if you have a red line on the left of your rung, that means there's a problem with it. So if anybody's having any red lines or any issues finding things, that would be a good chance to speak out before we get too far ahead. Okay, awesome. Our next control philosophy condition is the stop push button will take the plant out of run mode. I think by this point, you guys are probably capable of programming that one yourself. So I'm not going to annotate what I'm doing here. We'll add a rung, we'll add our stop button, and we'll add an output to satisfy that condition. But if you want to see how I do it, I'm going to be doing it on the screen here. Okay, anybody need more time? Okay. The next condition in our control philosophy is while we are in run mode, the pump will turn on whenever the water level is above the high set point. The pump will remain on until the water level is below the low set point. So everybody's kind of got their own way of programming this fairly typical scenario. I am I'm going to tell you the way I do it, at least the easiest way I can do it. I wouldn't necessarily do this on a live system, but we will need to make two tags. We'll need a high set point tag and a low set point tag. And we're going to need to make sure those tags are retained because we don't want the operators having to go back and change this set point during if a power loss ever occurred. So we're going to shoot a rung below at the bottom. And if you want, you can toss a couple in there just to keep things simple, speed it up down the road. So while we're in run mode, which our run mode bit will be true for, if our tank level is greater than the high set point, so we can use a comparison instruction for that. And I'm sure you can figure out where those are in the toolbox here. Everything is alphabetical. So in our comparison category, we have your usual less than, greater than, not equal to, equal to. So we want a greater than or equal to. We're going to put it on that rung. The value we'll be comparing from is our tank level scaled. And we want to compare it with our high set point tag that we haven't created yet. Since this instruction, if you mouse over it, accepts any elementary data type, when we create this variable, it's going to ask us the data type in addition to being local or global. This is one of those instructions that will take any elementary data type, so we will have to specify the data type. So high set point, I'm just going to call high underscore SP. We'll make that a global variable since we'll put it on the HMI later. It's going to be a real data type. And for the comment, if you guys want, you can call it the HMI set point. Anybody need more time? So we're going to add an output to that rung. So we can, now I haven't talked about this much, but you have probably noticed these green sort of shortcut buttons to commonly used ladder logic instructions. This was a relatively new feature, and some of you are on older software, but if you have these green boxes in front of you, you can simply click on output and it will drop an output on the rung as well. If you don't have that, you can work from the toolbox, you can use hotkeys, you can even right click on the rung and it has all of those for you as well. So input, output, function, function block, that kind of thing. So we want to turn on the pump if we're above that. So this will be our motor start, I think we called it. Yep, start motor, sorry. So our start motor, and we're going to want to set our start motor. So we can right click on it and choose a set instruction. And now I'm going to copy and paste this whole rung. So to take the content, the contents of an entire rung, we click to the left of the rung where the number is here. And we can copy and we can paste in the same spot. And we have that same rung again. Now for the turning off the motor, I'm just going to change this greater than or equal to instruction to a less than or equal to. And I can do that just by clicking on what that mathematical comparison is. So I'm going to change it from a right bracket to a left bracket, and that will change that to a less than or equal to. Then we can change the high set point tag to a low set point tag, which we'll have to make. And if you recall, it's a real data type and a global. And then finally, we'll make sure that that resets our start motor bit. Now, some of you might be thinking this is kind of a bad programming practice because if we stop the plant when we've latched start motor, that motor will stay on because we used a set instruction. And you are correct. So if you want to put logic to mitigate that, you can. This is a simulated lift station. Obviously, we're not really accommodating kind of real world issues that we might run into, but just a caveat there. We wouldn't do this way in the real world, but so for our next condition, if we, in the event the level switch is triggered, we stop the plant and we set an alarm bit true, which we'll get to flashing the button in the beacon at the end here. But so we're going to have an alarm bit and we're going to make sure that we take the plant out of run mode. So we'll need an input, which will be our LSLL. And now in Sysmac Studio, we can have paralleled or seriesed outputs. Really, it does the same thing. It's a matter of preference. So if we wanted to parallel these, I'm just going to make the first one run mode. That'll be our reset instruction. And then we want to set a bit so that it remembers it had this alarm at some point. So I can, if I drag a coil on top of something, it's going to create an OR condition, a parallel output. If I drop it beside it, it will do it kind of in a series fashion here. So you can have any mix of paralleled and series output instructions in a rung. The only catch is you cannot have an output condition, then an input condition, and then another output condition. So if we wanted to parallel it, we just drag it on top of the existing condition, and it's going to parallel it like you see here. So for this one, we're going to set an alarm bit, which is LSLL underscore alarm. And since it's never seen that before, it's going to ask us if we want to make it an internal or a global. We'll make it a global because we'll have it on the HMI next class. That's also going to be a set instruction. So I'll give everyone a second to do that. Okay, does anyone need more time? Good. So the next one is the motor fault input, and we're going to be doing essentially the same thing with it. Take the plant out of run mode, but we're going to set a motor fault bit. So it will likely be easiest to just copy and paste this whole rung. Control C, Control V works. You can right click on it as well. And instead of the level switch, it will be our motor fault. And we're going to make a bit for motor alarm. Now, if you accidentally make something an internal when it needs to be a global, we can, from the top of the logic here, there's a variables category, and it lists all of the internals and externals that you're using in this program. And we could take something that's an internal, we could right click on it and we could move it to global and vice versa. So give everyone a second to fill in the motor fault rung. Okay, we're down to our final 2 or 3 rungs here, and then we get to simulate it, which is pretty fun. So for the next rung, we have the reset push button will clear the errors if conditions allow. So in our logic, we'll start off with a contact, and it'll be our reset push button. And we're going to have an output to reset those alarms. So we can make one for our LLL alarm. And I'm going to Control C, Control V, LSLL alarm, and it's going to make it a parallel scenario like this. If you create the parallel rung first, it's going to be a bit easier. You can shift things around and customize it by dragging and dropping your conditions, but setting up the parallel first when you know you have preceding conditions saves a bit of time. So the first one will be for the LSLL alarm. We'll also need one for our motor fault alarm, which is motor underscore alarm. And these will both be reset conditions. So we can right click on the output, make it a reset instruction. And now if the conditions permit was one of the caveats in the control philosophy. So we don't want to reset the level switch low alarm unless the level switch itself is in its normal state. So we'll have a contact for that. And we want that inverted since that needs to be false in order to reset this. And the same thing with our motor fault. We're going to want that inverted as well, / if you're a hotkey programmer.
Real quick on line 1, can you scroll up to line 1? Okay. I had one of them inverted that I shouldn't have. Thanks.
No worries. Okay, and our last condition in our control philosophy is the LEDs on the buttons and the beacon will reflect the mode. So green, which is our start push button LED. When it's solid, that indicates that we're in run mode. When it's solid red, that indicates we're stopped. And when it's flashing, that indicates we've got an alarm condition. So this one, when it comes to the flashing part, I will show you guys how to retrieve pulsing 1 hertz system clock that we can use for this. So if we are in run mode, our green LED, our start push button LED, is going to be solid. So this is a very easy one because our run mode is solid. It's always on. Let's see, I think it's the start LED. Yes, start LED. So that one we can map directly to our start LED. Now, if we're not in run mode, we can make our stop LED on. But now what we need to do is we need to figure out since we can't have duplicate outputs for a single bit, we can with set and reset, but we cannot with the output. It causes problems. We need to make this rung accommodate the alarm conditions and flash that as well. So I'm going to see if I remember how I did this before. So if you're wondering where the system clock pulse bit that I'll be using comes from, it is in, and I rarely get it out of the toolbox, so give me a second to find it here. Let's just try this. It's in the other category. Okay. So in the other category, there's something called get 1s CLK. So where we want to use that pulse, we'll put the get 1s CLK bit. And that should satisfy our LED flashing when there's an alarm present. So I'll give everyone a second to copy that run. So how this sort of reads out logically is, if we're not in run mode, we don't have our low alarm or our motor alarm, that LED will be solid. If we have either of those alarms and we're not in run mode, then we're going to pulse this get 1s CLK. And you'll see how this works when we're simulating here in a second. So I'll get everyone to fire up their simulators now. So to do that, up at the very top in the Windows menu, we have simulation, and we can run our simulator. So the first time you start up the simulator takes a bit longer than sequential times because it has to build the virtual PLC. I'll give everyone 30 seconds or so to get your simulator started up. Okay, does everyone have your simulator started up? If you had any logic errors, then your simulator will fail to start. You do need to clear any errors in your code before you can run the simulator. Okay, good. So in our simulator, if we want to simulate something on a bit, on a Boolean instruction, like an output or an input, anything tied to a Boolean variable, we can double click on it, like I'll do on the start push button here, and a little window will pop up and it will tell you the current state and it will give you an option to toggle the state. So I'm going to simulate pressing my start push button. So if I double click on start push button, I can change that to true. And then I'm going to take my simulated finger off the push button and make it false again to make sure that it will stay in run mode. Now this look and feel, I should add, is identical to being online with a real PLC. The only difference is you don't have to worry about physical I/O. You simulate those states. So for Boolean variables, I showed you we can double click on them, change their state. For numeric values, like our high set point and our low set point, we double click on those. Instead of having true and false, we have an actual value to enter. So for our high set point, I'll get everyone to double click on high set point and enter 75. It'll be 75%. And for our low set point, I'll get everyone to enter 25. Now, since our tank level scaled value is coming from the scale transformation block in the other program, writing to tank level scaled won't do anything because it will be overwritten automatically. So what we need to actually write to is our tank level raw. And to make it so we don't have to keep jumping back and forth between our analog program and our main program, we can use something called the watch window. So everyone can go up to View, Watch Tab Page, and we're going to add the variable tank level raw to our Watch Tab page. And now that's going to be permanently pinned to the bottom of our Sysmac Studio IDE. So we can now go over to our logic, and when we want to change our tank level scaled, we can just type the value here down at the bottom in tank level raw, and we don't have to jump back and forth. So the scaling is 0 to 8,000. So 75% would be 6,000. So if I make it 4,000, a value of 4,000, that'll put us at 50%. And you can see the variable value change to 50 on our scaled. If I want to bump it up to greater than 75%, I'm just going to put it to 6,500, hit enter. And I'm working in the modify part down at the bottom here. But you can see it started the motor, and then I'll put it back to 50% to simulate the tank draining, which is a value of 4,000. The motor stayed on. And then when we drop below 25, which would be a value of 2,000, it should stop the motor. So I'm just going to put 1,500 in there. And that stopped our motor. So far, everything in our control philosophy is checked out. The other thing we'll check now is our alarms and our LEDs. We didn't do anything for the beacon, but we can just drop the beacon right after this get 1s clock bit, and it's going to work just fine. So for our level switch low, we can double click on the level switch low. And if you would rather work out of your IO map, that's a possibility as well. So we could actually go into our IO map. We can see the values of all of our Booleans and all of our integers, and we can actually forcefully change them here too. But since we're simulating, it's easiest to just do it in logic. We don't have to force the values. So we'll trip the level switch low, and we confirm that it took us out of run mode. We can see that's false. We can see that our stop LED is now flashing. So the logic for the motor fault is pretty much identical to that. So we don't need to test that because we are out of time, but I will stay on the call for 10 minutes after this, if anybody wants to hang out, if you're having any issues, any questions, I will be here for 10 minutes. If you want to keep simulating and playing with it, you can go right ahead. The only modification that we're going to make, and we can do it at the start of next class, is we're just going to add the beacon right here after the clock bit, so it behaves the same way as the stop LED in an alarm condition. So if you need to jump off, jump off. If you want to hang on for 10 minutes, I'll be here for another 10 minutes.